In this lecture, we will be covering routing. And so this is kind of covering the basics of routing, especially with two hydrologic routing techniques. There's an accompanying Excel spreadsheet and that you can follow along with to carry out these calculations. Another interesting kind of beginning of this is to sort of look at what a flood wave looks like in real life, and you see the link there that you can watch as an example. So we're going to talk generally about what the concept of routing is and why it's important, and then we're going to kind of cover the different types of routing that is out there, and specifically diving into two different types of hydrologic routing, level pool routing, and the Muskingum method. And so a lot of the times when you're studying hydrology, you are working on having flow and an outlet of a watershed or a catchment. And so the rainfall is collecting on this area of land, and you care about what goes on at the outlet of that watershed. And specifically, you're looking at flow through time at one particular point in space. So the outlet of this watershed would basically go into this river, for example, and you have the flow as a function of time that appears right there. And so this is really, this is a good thing to do. But you can imagine that for the purposes, say, of flood forecasting and of other sorts of issues on a river, you want to know sort of how that wave of water is going to propagate down through the river to get to a point downstream. So specifically, in this problem, we're going to assume that we know the flow coming in, and then we use routing to give us the timing and the magnitude of the flow that occurs going downstream, okay? And so this is also going to look like a hydrograph, right? But after you do this kind of transform, you're going to figure out what the timing and magnitude of the flow is downstream. You can imagine that there's two broad sort of ways of doing this. And I'll start with the second one first. So if you solved the equations of open channel flow, the river model, a HEC-RAS model, or what have you, you'd be able to not only tell me what is going on downstream, but you'd be able even to sort of tell me what's going on at all different points along the river. This is distributed because it means that it is explicitly given in space. And overall, this is a really good way to do this kind of calculation. However, a lot of the times in sort of design circumstances and other cases, you may not have all the information about the river that you need, and you need something sort of simpler in order to be able to kind of treat the river like a black box and just say, I have something coming in and I'm going to parameterize what's going on in between and then give me a flow going out. And that is what hydrologic or lumped routing is an ability to do that. So you know the flow upstream and you call that I or inflow. You're trying to find the flow downstream, and you use some kind of relationship between storage and flow to figure that out. And that is important because mass balance is not going to be enough for you to actually solve this problem. You need an extra piece of information. In this particular class, we're going to cover two methods: level pool routing and Muskingum routing. If you look at this operationally, you see that one of the extra kind of steps in this process is the conversion between flow and stage. So, if you're forecasting, say, the height of water in the river at point A, you have stage as a function of time. You use your stage discharge relationship then to get discharge as a function of time. And routing, the input, again, is the discharge over time, and then the output is the discharge over time downstream. And most likely the shape of this is going to change, as you can see. And then you can basically use the process in reverse to get stage as a function of time. And this is how flood forecasting is done. And you can imagine that there's a lot of different applications of this. Water management models where you're moving water from place to place, and you have to have this kind of treatment of the timing of the conveyance of water. You use routing for this. When we look at this in the purpose of sort of seeing this with respect to time, okay, we've got inflow, we've got outflow, and we've got storage. And so the idea is that the the outflow hydrograph ends up having a lower peak, okay? And it's generally more spread out than the inflow hydrograph was. And the reason why that is because either the reservoir or the river, you can use the level pool approach for both, whatever is going on in between those two places is actually storing water, right? And so we know that the change in storage with respect to time is equal to the inflow rate minus the outflow rate. And when we're working on real world kind of discrete data that has time steps associated with it, we use a finite difference approach to be able to give us that continuous differential equation, but in chunks of time that we can work with. Okay, so you have this very small delta t, and you're approximating what that integral would be. You've got 2 points in time, so index j and index j plus 1. Okay, and so over the course of that small amount of time, inflow is coming in, outflow is going out, and then you can use the inflow and the outflow to determine how much water has been stored in between those two times. Okay, now, given the problem statement that we have for routing, here's what we sort of know and what we don't know. You can think of the kind of famous example of that you have an inflow of a flood wave that you're trying to put through a reservoir. And so if you knew what that flood wave was, then you can assume that you have inflow for all time, okay? So that's known. So you even know ij plus 1, you know inflow at all times. So positive smiley face, good idea. But you only know outflow and storage at the current time, okay? Because what you're trying to figure out is what's going on, what's going to happen in the next time step. And so when we take the finite difference approach equation, we can rearrange it into a part that we know and a part that we don't know. Okay, so the unknowns are on the left, 2s j plus 1 over delta t plus q, and then the knowns are on the right, all of the i's plus the j and the q, the s and the q at the current time step j. Now, you have this equation and all this is well and good, but the problem is that you have two unknowns and only one equation. So the conservation of mass is not going to get you where you need to go. And so let us tell a tale of two hydrologic routing methods, okay? So we've got this equation, and this equation at the top of the screen is valid for all, this is conservation of mass, so it's valid, and it's valid for both of the methods. But the second piece of information that we need is we need some relationship between storage and flow. And what that'll allow us to do is it'll allow us to either sort of break up the party on the left-hand side of the equation, or you could just basically make a more simplified assumption about what's going on with storage in your river, and then you could use that as that relationship. And so to kind of parse this out, level pool routing is basically an approach where you develop this relationship between the 2s over delta t plus q and q, right? And I've removed the subscripts here at the bottom because what this ends up being is a lookup table that is valid for all time. Now, with reservoirs, we sort of know what this looks like because we know storage and flow relationships for reservoirs that are controlled by things like spillways and other kinds of outlet works. But you can also use this for rivers as well. And once you have that kind of lookup table, then you can use that to interpolate what the value of Q is, given that you have the chunk of the equation that you've calculated, and then you can use that to finish the routing equation. The second approach that we're going to talk about is Muskingum, where you have this artificial relationship where you assume that the storage in the river reach that you're working on can be approximated by a wedge and a prism. Okay, so there's going to be other equations and new parameters that are going to be introduced that you're going to be able to plug into the mass balance equation and be able to then determine what the rest of the flows are. Okay, so with level pool reservoir routing, the first method we're going to talk about, the given information is the inflow hydrograph and then the storage outflow characteristics. Most of the time, these storage outflow characteristics are not going to be sort of tied in a bow in a nice way where it's going to give you exactly 2s over delta t plus q. You have to calculate that for yourself. But then once you have that, you're going to be able to use that for your interpolation. You assume a hypothetical reservoir with a horizontal water surface. And so, this works well for reservoirs, but for streams and rivers, you have to be a little bit careful because there's some recommendation that if the river is too shallow and you have some kind of backwater effects, or if the inflow hydrograph is too sharp, it's too rapid, this method is not going to work, okay? But for other situations, then this method is okay. So you have the given and assumptions, then you want to find the outflow hydrograph. So here is the approach, and I'll pull up the equation again for reference. So the approach that you are using is one in which you take this equation and you sort of run with it initially. So we know all of the stuff on the right-hand side. So the first thing you can do is just calculate ij plus 1. And you can do that, and that's easy. After that, then at first you have initial conditions that are going to give you Sj and Qj. So you're going to know this. And then later you're going to be able to find that, say, from the previous time step. So you know all this. So the first thing is just to do the first part of this equation. The second one is to take that and add 2Sj over delta t minus Qj, which is here. And then that's going to give you this guy. So 2Sj plus 1 over delta t plus Qj plus 1. Okay. Now, it's too bad that you're not done here, but you are not done because you don't know what sort of percentage of this is associated with the storage and what percentage of this is associated with the outflow, okay? And so what you can do is you can use that storage outflow relationship that you have for your reservoir, for your river, to be able to create this lookup table where you can interpolate for the value of Qj plus 1. Once you have that, the kind of puzzle portion of this is over because you have Qj plus 1. And remember that when you are at a current time step, at the current time step, when you find Qj plus 1, that is equal to what Qj is at the next time step. So in step 4 of this procedure, you're already getting ready for the next time step. So what you can do is just take, what you need to find at the next time step is this, 2Sj over delta t minus Qj, right? But we haven't switched time steps yet, so it's still j plus 1. But you need to find this. So if you take the new shiny Qj plus 1 that you found, multiply it by 2, and subtract it from what you already have, that's going to then give you what you need for the next time step. And then you move down to the next row of your spreadsheet or the next iteration in your computer program, and then you go to town. Because now that you have essentially what the new 2Sj over delta t minus Qj is, you can just add that to this, and you end up getting the next value for your method. Okay. I will show you how to do this in Excel, which hopefully will clarify this procedure, and we'll kind of come back to this procedure. But as I mentioned, on the next slide, we're going to talk a little bit more about these kind of lookup tables and sort of how to do it, and a clever method in Excel that'll help you do it in a rapid sort of way. Okay, so, and I'll just kind of I'll show you the spreadsheet real quick. So, in the kind of blank spreadsheet which you have access to, I have already done the work for you here, but it's really just a matter of plugging and chugging. So this is going to be developed for, say, your reservoir from the idea that you know sort of at each level of storage what the outflow ends up being. So imagine that you're working on a reservoir. If the height of a particular spillway, say, is equivalent to where the storage is equal to 80 million cubic meters, then if the spillway will release 50 cubic meters per second, for example, then that's one of these rows of your relationship. Now, once you have these, you can figure out what 2s over delta t plus q is by simply doing this manipulation. Now, the only tricky thing about this is units. And so people get confused about the units, but the units are really pretty simple because you just have to remember that the units that you're calculating need to be consistent. So you've got Q in this equation, and you know that Q is being given in cubic meters per second, which means that storage needs to be in cubic meters and the delta T needs to be in seconds, right? And so I have already kind of populated the delta T in seconds here in this spreadsheet, as well as multiplying to make sure that my units work out, because you know, here I have the units of storage in million cubic meters. Over here I have it in cubic meters, but whatever you do, just be consistent and make sure that this number ends up working out as far as the units are concerned. So now that you have this, the first step is really to create the yellow column of your table, right? And then you're going to be able to use that as a lookup table, okay? And so you go here and then you have found a 2s over delta T plus Q, because you know that from that conservation of mass equation. You go up, you use the lookup table to find where it intersects on the line, and then that's what the Q is that you are using. And as I mentioned, when you're doing this for a reservoir, what you would have is you would first have some kind of depth versus storage relationship. And then a storage versus outflow relationship is going to tell you essentially how that reservoir is going to respond to a particular amount of water in it. You can do the transformation we just talked about, and then you relate Q to 2s over delta T plus Q. So what we'll do now is we'll talk about how to do this in equation form, then we'll talk about it in Excel, and then we'll kind of go through what the example looks like. So you're doing a piecewise linear interpolation here. Credit to this link that gave me the idea for how to do this. And just in mathematics first, you know, your x, quote unquote, is 2s over delta T plus Q, and then the y is your Q, and you're referring that to the lookup table here in the upper right-hand corner of the screen. The tricky part about the piecewise portion of linear interpolation is trying to figure out which rows to use in the table. So in our example, we'll just use rows 2 and 3. And so, you know, it's just a simple equation essentially to find what you're interpolating between. Notice that the coefficients here relate to the rows that you're using in the table, so you can see this. Now, x is going to be from the time series calculation that you're doing. You're going to end up being able to find y, and then you're going to be done. I've kind of color-coded these for the y lookup and the blue lookup, which you'll see in a minute when we do the Excel version. Okay, and so the trick to this is really to use this automated procedure for finding the rows between which you end up using to interpolate. Okay, and so those are the two new equations that we're going to be introducing. All right, and so in the Excel sheet that I shared, you already kind of have it set up somewhat where you have F3 being the 2s over delta T plus Q that you found. And I added a new column, G3. G3 is going to be the row of the table that you can look up, and just to give you a peek at it, you can see this spreadsheet that I've set up. And so the row for interpolation is going to be right here, and it is going to be stored there. And then you're going to use that row for interpolation when you actually get into the equations, because what the first thing it's going to do is the match function basically says, if I have a list of data and you give me something that's going to fall within the range of that list, I'm going to tell you what the first kind of a floor calculation, the first value of the two that it is between, okay? And that's going to be match. And then you're going to be able to then calculate the answer, which you're going to store in H3. And you're going to use the index function. So once you know what row you need to be, the index function essentially says, I'm going to give you a list of variables, and then you are going to tell me what the second one is. Now, if you're using a computer program to do this, we use indices for arrays all the time, and it probably is a little bit more straightforward, but you can actually do this in Excel just following the syntax that we're going to talk about here in a minute. Okay, so this lookup table is going to be on the right-hand side of the Excel sheet, and then the time series are going to be on the left. You could also have the lookup table in a different tab if you wanted to have it or whatever. So the first row for your lookup is going to be the equation for G3. So you're going to have this match. And given the list of your X's, where does the X that you are really going to be working on, where is that going to be found? Okay, and so this is the X, and then you have the list. And then G3 will be able to be used in the other equation. So we remember the interpolation equation that we have, and when we put this into Excel form, you can kind of follow along. So the first one is that, so the value that we're looking for is going to be equal to the Y in the first of the rows we're looking at, in row 2, for example. And I want to know what the value of the second value essentially in this column is. And so I say index, I give it the data, and then I say I want the second one, or whatever G3 tells you. So that's Y2. And X2 is going to be the same thing. So you've got X, which is here, minus X2, which is just a lookup in the X row. And then, I have this fraction here. The only difference is that, to get Y3, for example, you just say G3 plus 1. And, Y2 would just be related to G3. So the Y's and the X's, okay? So the cool thing about this is that once you set this up, then it'll just be valid for all of the time that you're doing your interpolation. You do not need to manually sort of go in and figure out which 2 rows that you are between, like the way that, say, I used to do it when I first learned about this, but this is going to be a lot slicker for you. It also mimics very much the way that you would do it if you did it in Python or R or something like that, where you would have this table that would have your information in it. You would have to find a way to figure out which row that you would be between, and then you just code up the equation for doing the interpolation. So the example then is as follows. So we have time step of 1 hour, and we know that there's a time step of 1 hour because the data that I've given you is separated into different hours, right? So we've got this flood wave coming through a reservoir, right? And I need to route that inflow hydrograph through a particular reservoir that has the properties that are shown here in table 2. So at first, essentially, you would be given the storage. Maybe you would just be given height versus storage. And maybe you would have to figure out what the outflows are, or you may know what the outflows are already. But take whatever information that you have, and you have to process it in order to give you what that you need for your actual lookup table, okay? And we'll show you about that. The other thing you have to be careful about is your initial conditions. So you know that the reservoir has an initial storage of 70 million cubic meters. Now, conveniently, 70 million cubic meters ends up being a flow of 0. However, do not always assume that the initial flow is 0. You could have been given, say, that the initial storage is 100, which means that the reservoir is already releasing water before the flood wave even comes in, okay? And so if you needed to do that, then you would need to interpolate here to figure out what your Q is before you would go on, okay? But here it's a little simpler because you already know what the initial flow is. Okay, so I would suggest that potentially you pause the video, go into your blank Excel and try to figure it out. Try to sort of work on the equations before you continue on with the video, just so you have some time to kind of digest it yourself. I'm going a little fast, but once you do that, come back, and now we will go through how to solve it. Oh yeah, I forgot my animation here. So you create the 2s over delta t plus q table first, set up the equations, do the piecewise linear calculation, and then at the end you're going to want to make plots just to kind of show what the answer is, okay? And so the blank sheet that I have made available basically has the inflows that you're working on. It has J's and the times already filled out, as well as the initial storage. And I actually even did the storage rating table for you. Again, remember to do your unit conversions there. You don't have to make a plot, but I just made a plot for the purpose of the of the slide that basically just shows what the lookup table looks like. Okay, now to kind of just quickly go through what the how you actually work this out. Now in the slides, I actually have a screen capture of these answers so you can kind of follow along yourself. But basically the way you set it up is we'll kind of go through maybe 2 rows of this. So the first is that you've got your inflows. The first thing that you do is you just say ij plus 1. So that's C3 plus C4. Pretty easy, and then you go all the way down, okay? Now, after you have this, then the next thing is this 2sj over delta t minus qj. Because it is at time step j, it is assumed that you know what sj and qj are, okay? And so I just kind of put my initial conditions up here at the top of the table. So I just relating 2 times my storage divided by delta t in seconds minus my initial flow. Now this is the only one of these where it's going to be different in the first row than in the second and the subsequent ones, because when we get to the next row, we're going to, we will have this information from the previous time step, right? Because one man's trash is another man's treasure. This row's j plus 1 is equivalent to this row's j, right? Okay, so we have that. And so then D plus E equals F. And I can just bring up my example from before. Again, we know from this equation then that you can just take these 2 guys, add them together, and then you end up getting that big chunk, right? So 38,989. We do not know how much of that 38,989 is equivalent to storage and how much of it is equivalent to outflow. And that's why we need the interpolation. So I set up this row for the interpolation using that match again. I want to know my X, which I found. Where does that X fall in the data of all my X's in my lookup table, right? And it so turns out that, and it kind of makes sense, we know that the storage is, it's going to be within the first 2 rows, right? So row 1. And then, you do the equation that I showed in the slides that basically figures out, the X's and the Y's out of my lookup table and then calculates what the value is. Now, a way to check to make sure that you're right is that H3, which is the Y, quote unquote, of your lookup, that this should fall within the first 2 Y's. If it doesn't, then you did something wrong, right? Because you're just doing interpolation. You are not doing any kind of extrapolation here, okay? Now, there's a couple of different ways to move forward. I mean, you should congratulate yourself first, because this is kind of the tricky part and you have found what you needed to find. What we talk about in the slides is the idea that you should be able to go and say, all right, there's different ways of kind of doing this, the kind of algebra for what needs to come next. The one thing you could do is just pop down to the next row already and say that if I take this, okay, so the j plus 1 in the previous step is the equivalent to j in the current step. So I'm already kind of halfway there. I can take F, what's in F, and subtract 2 times what's in H, and then I'm going to know sort of what I have. A little bit more straightforward is to just actually find what the storage is, and that can be useful anyway, because if you want to make a plot of storage, you're going to need storage. Normally you wouldn't need to figure this out for the purpose of just making the equations work, but it's good to have it. So same kind of algebra here. So for Sj, right, it is simply, again, what you have here, just minus 2 times what you have found. Sorry, I was getting ahead of myself. So it's this, and then you just do the algebra to solve for Sj. So it's F3 minus H3 times delta T over 2, and then you end up getting the storage. Okay, so now that you have the storage, it makes this next equation, you can either sort of do the subsequent rows as a function of the previous row, or vice versa, right? So or actually you always do it as a function of the previous row. But it's just a little bit easier for the algebra because I don't have to solve for this. So, you know, it's just 2 times Sj over delta T minus Qj. So it is 2 times 2 times this S that I found. And remember what happens with the subscripts. And then the H that I found, again, remember the subscripts. Okay. And then this is going to be valid for the rest of the time, which is good. And actually, at this point, you're done basically, because we've already kind of stepped through. Your interpolation is going to work for all the rows, and you're going to end up getting something that looks like this. Now, what you'll notice when you graph it is the idea that what it's going to look like is it's going to be this kind of huge inflow, and then the reservoir is going to release water very slowly. You can tell that because if you look back in the storage rating table that you have, I mean, look at the maximum outflow when the reservoir is at this level, okay, is 700 CMS. So that's quite a bit lower than what the inflow is. And so hopefully there's enough storage in your reservoir basically to weather this particular storm, okay? One of the ways that you can also do this too, and the way that you would kind of look at this in an engineering context, is you would probably be configuring your outlet configurations to try to weather a particular inflow hydrograph, right? So you might be adjusting this relationship in order to make sure that your reservoir doesn't overtop. Like you never want the S to go above the top of your rating curve here. So, you know, the other, you usually don't have much control over inflow, but maybe you have a diversion upstream of your reservoir that you can kind of kick in to sort of reduce the peak a little bit here. So that's basically the level pool routing procedure. Once you have a spreadsheet like this set up, or a script set up, then it really is just plug and chug with different levels of inflow as well as different storage outflow relationships. Okay, so let's move on to hydrologic routing method number 2. This is going to be useful in situations where you don't have a lot of information. It is used for river routing and not so much for reservoir routing. But it really just, similar to a lot of these other engineering hydrology kind of applications, it is a method that relies on few parameters, and it you know, so it can be used in situations where you don't have a lot of data. All right, so the way to kind of get started with this is, let's sort of start simple. If you have a situation in a steady state condition where the inflow rate is equal to the outflow rate, which hence why it is steady state, right? Then you can think about the storage in that situation as being, you know, this change in storage with respect to time here is going to be 0, okay? And thus, the storage volume is just going to be constant, right? So if you were in a river and it was the world's most boring river and the flow is never changing, you could just model it using this simple prism, okay, that has a constant storage, right? So steady state means that I is going to be equal to Q for all time. And so like you can then say that the storage is simply a function of either the inflow or the outflow because they're the same. And remember your units, right? So the inflow and outflow are going to be volumes per time, okay? And thus, if you want to have a volume as your storage, then what it's going to end up being is that K parameter is going to have units of time, right? So flow per time multiplied by time ends up being, or sorry, volume per time multiplied by time ends up being volume. So that's the easy part, is this wedge part where, you know, you can imagine that in certain times the flow is not going to be changing that much, and so it makes sense to have this prism. But there are other times where, you know, it is not as easy to just say that the storage is going to be constant, because we know based on the previous example that it's not. And in fact, you've got entering, and you've got entering inflow, and then some release from that inflow that occurs later, right? So there are two kind of big conditions that occur in that famous inflow outflow graph that we always look at, is that you can kind of compare what is going on, the magnitude of the inflow and the outflow, okay, coming in. So like there's a period of time when there's more water coming in than going out. And so the amount of storage is increasing. And then at some point, the opposite is happening and there's more outflow than inflow, and there's a release from storage. There's a loss of storage basically, and the storage is going down. Okay. Now, so like what is the most simple way to think about this is just this kind of triangular sort of relationship where you've got increases coming in and then a decrease going out. Okay, so the wedge prism sort of model in Muskingum says that you start with this prism of storage, okay, and then you've got a positive wave basically coming in because inflow is greater than outflow, and then a negative wedge when the opposite happens, when outflow exceeds inflow. Okay. Now you can imagine, and you may be starting to see that the mathematics of this are pretty easy, because if I just have this relationship between inflow and outflow, right, then if inflow minus outflow is positive, then the wedge is positive. If outflow is greater than inflow, then inflow minus outflow is going to be negative, and then the opposite will happen, right? And so this is how Muskingum gets away essentially with only having two parameters, because you have something that kind of controls what that wedge looks like. And then we already talked about this K in the prism approach. Okay, so just to kind of look at this in a schematic kind of way, we've got this situation where you've got this prism, right? And we know then that like it's kind of be constant and it's kind of hanging out. And then, so in the case when I equals Q, then the prism is there and it's not very interesting. But then in a case where I is greater than Q, you see that there is a part that is represented by Q. So like this part is constant, right? Because, you know, Q is the same as Q. And then we know that I is greater. So then there is this extra little piece, okay, that is up there. And there is some storage that is associated with that. Then when we look in the opposite case, it's the same kind of thing. We know that Q is going to be bigger. So if you were to just extend what that prism would look like, it would look like this. But then there's this extra piece where if you subtract Q from I, then you get this other piece, okay? Now, we know that the first part of the storage is just going to be K times Q as usual, and we need to figure out what the second part of that storage is, okay? And what ends up happening is all it is just S2 equals K times this new parameter X multiplied by the difference between I and Q. And again, the sign sort of works itself out because of the relationship between I and Q. In both cases, you can just add the storages up. So storage is just going to be equal to the total storage is just the wedge plus the prism. Another way to look at it then is this, you know, the diagram on the left. And again, you can see the prism and the wedge are going to be playing off of one another depending on the relationship between I and Q. And so, you know, like Bob Ross would draw, you know, again, the Muskingum method is really in a situation where the reaches need to be stable, because there's nothing there's nothing to model changes in that relationship. And then a simple stage discharge relationship, you can imagine again that if you have really strong, like really quickly changing inflow hydrographs and stuff, that this is not going to be as good. Two parameters. So the first is X, the weighting factor for the volume distribution between the wedge and the prism. Okay. And so, you know, like it goes between 0 and 0.5. If you have 0, it's just there's no wedge, right? Because the storage ends up being, you know, it just equals the prism. Okay. And then, so as X increases, then you're going to have more of that relationship between, you know, like a higher percentage of the volume is going to be associated with the wedge. Okay. a default parameter that you can use is 0.2. And some sensitivity studies have shown that the value of X doesn't necessarily matter that much on the results of this method. But the parameter K is probably more important here. And you can think about this as this kind of travel time sort of constant that you have. And the larger, in my very artistic drawings there, essentially the larger the K value is the more time it takes for the peak to move in, and the more amount of attenuation that you end up seeing. So let's take a look at the mathematics of this. So in the Muskingum method, we know that the storage is the sum of those two components that we talked about. So the wedge plus the prism, and then of course with a negative sign on the wedge if necessary. So what we're going to do is we're going to take this new sort of geometry that we had. This is that second equation in this situation where we have these, we have two unknowns, we need two equations. So we rearrange, just as a kind of, we rearrange this such that it is just a function there of the coefficient K. And, so that's good. We have relationships for storage, which is great. But what we really want to know is we want to know sort of what the relationships are between storage and flow. And we are going to plug these things into this finite difference approach that we used before. We're going to rearrange the finite difference approach a little bit because of the way that we've sort of set up the storage equation. But regardless, this is going to be the kind of fundamental equation that we're using to get us to the finish line. Okay. And so I'll just add I'll add subscripts to these storage equations. And so you have Sj and Sj plus 1, where I'm adding these subscripts to I and Q. Now remember, of course, that we still know what I is for all time. So we know Ij and we know Ij plus 1. Okay. But now what we need to do is figure out what Qj plus 1 and Sj plus 1 is. Okay. So the change in storage is now just simply K multiplied by those two terms in brackets subtracted from one another. And that is, Sj plus 1 minus Sj. And then we bring back in continuity. We've rearranged continuity such that we have that Sj plus 1 minus Sj. And so it is the Ij plus 1 over 2 multiplied by delta t, and then the same thing for Q. Okay. And so now we can basically eliminate the left-hand side of both of those equations and rearrange in a similar fashion to what we did before, where we are, keeping track of what we know and what we don't know. And the cool thing is that what ends up happening is that K and X are constant, and delta t is also constant. So you can create yourself these different coefficients that are used to sort of set up what this would look like in a spreadsheet or in a program. And that's what we have here. So once you combine those two equations, what you can do is create these easy coefficients that add up to 1. And those coefficients then are basically a weighted average, essentially, of what information that you already know. So, one more time, remember that we know what Ij plus 1 is, and Ij, because we know I for all time. And we know what the current flow is because it's at the current time, okay? Multiply those things by these three coefficients that never change, and you can figure out what Qj plus 1 is, okay? So setting this one up in a spreadsheet is a lot easier because it really is just a weighted average of information that you already have. Okay, so the example will kind of run through in a similar fashion to what we did before. So you've got an inflow hydrograph here, and if you use parameters x equals 0.2 and k equals 1.4 for a time step of 1 hour, okay, here's how you do it. So you have all of your parameters. You're going to put them off to the side because none of them will change. You can calculate your C coefficients, set up a column for QJ plus 1, and then go to town. Okay, so this is what the solution looks like, but let's pop over to the Excel real quick and sort of see how we do. Okay, so the blank version is going to have the parameters filled in, and it's going to have your rows set up for you. Sorry, your columns set up for you, and a place for you to fill in your constants. And so when we take a look then at what the answer is, so the constants are just going to be functions of the parameters that you have. Remember, your dollar signs basically to indicate that it is a constant, and so that you don't try to like drag down and expect things to change. The constant should sum to 1, and you can kind of test this. And it's a good idea. I put the equation in for all of them, but you could probably cut corners and sort of just say 1 minus the other 2 if you didn't want to do the final equation for C3. Once you have those constants, then you set up your time series. And so just as a sample, one of the things too is that I added a column for QJ. You don't have to do this necessarily, but I wanted a place to kind of put my initial conditions here. And I also wanted to be able to just make an easy graph between the two columns, right? Because it's all just relative to J, right? But I did this, and you can see then all it is just a linear combination of the coefficients and the other information. And then the last thing I'll say is that, and you know, like it's really important for us to know how to do these things and how to set up our time series and sort of understand how the equations combine. But, you know, there are definitely software programs and everything that will do this. And the thing to keep in mind is that routing is really an integral component to all sorts of water engineering models, such as HEC-HMS for hydrology, and in infrastructure models like Riverware, for example. You have these kind of travel time and routing calculations that are done. Even in hydrologic models like VIC, there is routing that occurs between the different grid cells and everything. So this is a really important skill for you to have, and hopefully you understand now what the basics of it are.